Hey everyone, and welcome to today's Explainer. We are diving into periodic table patterns and force energy synthesis. We're going to explore the absolutely fascinating journey that connects the incredibly tiny, invisible patterns of atoms all the way up to the macroscopic forces we interact with every single day. Let's get right into it.
Here's our game plan for today. We're going to start inside the atom, look at periodic table organization, check out atomic size trends and ion formation, connect atomic structure to everyday forces, and then wrap it all up with synthesis and transfer.
All right, Section 1, Inside the Atom, Visualizing Scale and Structure.
To truly wrap your head around matter, you first have to understand the absolute mind-blowing scale of an atom. I want you to think about the number 100,000. If an atom were expanded to the size of an entire football stadium, its nucleus, the dense center, will be the size of a single blueberry sitting right on the 50-yard line. That nucleus is roughly 100,000 times smaller than the overall atom, yet it contains almost all of the atom's mass. The rest of that massive stadium? It's literally mostly empty space where electrons just zip around.
If you've ever used something like the Build an Atom simulation, these fundamental pieces should look pretty familiar. Right in the center, you have your heavy protons, carrying a positive charge, and your uncharged neutrons. They both weigh about 1 atomic mass unit. Then, flying around the outside in all that empty space are the electrons. They carry a -1 charge, and they are so incredibly lightweight that it actually takes about 1,800 electrons to equal the mass of just one single proton.
Moving on to Section 2, Periodic Table Organization, Discovering the Rules of the Elements.
It's honestly fascinating how these simple subatomic pieces completely dictate an element's exact address on the periodic table. There are two main organizational rules you need to know. The horizontal rows, which we call periods, represent increasing energy levels. As you read from left to right, you are just adding 1 proton to the nucleus and 1 electron to the outer shell. Meanwhile, the vertical columns, called groups, stack up elements that have the exact same number of outer valence electrons. And because of that, elements in the same group exhibit very, very similar chemical behaviors.
Which brings us to Section 3, Atomic Size Trends, Measuring the Covalent Radius.
Because of how it's perfectly organized, the periodic table creates these super predictable patterns when it comes to the physical size of atoms. When you scan down a vertical group, the atom's radius gets larger. That makes sense, right? Entirely new electron shells are being added further and further out from the nucleus. But as you scan left to right across a horizontal period, it gets a bit counterintuitive. The radius actually gets smaller. Why? Well, you're adding more positive protons to the nucleus, which creates a stronger effective nuclear pull. That stronger pull yanks the electrons in that exact same shell closer together.
Okay, time for a quick pause check. Take a second to think about how these 3 elements, germanium, bromine, and krypton, compare in size. They are all sitting in the exact same period, row 4. Can you predict the order of increasing atomic size, so from smallest to largest?
Got your guess? The correct order is krypton, then bromine, and finally germanium. The reasoning here is pretty straightforward once you spot the pattern. Because they are all in the exact same period, the atomic radius decreases as you move to the right. Krypton has the highest atomic number of the 3, meaning it has the most protons in that specific row. That gives it the strongest inward positive pull on its electron shell, making it the most compact of the bunch.
All right, Section 4, Ion Formation, when atoms gain or lose electrons.
Now, atoms don't always just sit around being perfectly neutral. Sometimes they gain or lose an electron, and that sets off a fundamental chain reaction. First, they gain or lose a valence electron. Second, this creates a major imbalance between the protons and the electrons, which gives the atom a net positive or negative charge, turning it into an ion. And finally, that imbalance directly messes with the atom's physical footprint, either shrinking or expanding its effective radius.
The result gives us a really interesting contrast. When an atom loses electrons, it becomes a cation, leaving it with a net positive charge. Because it suddenly has fewer electrons but the exact same number of protons pulling inward, the radius becomes much, much smaller than the original atom. On the flip side, an anion forms when an atom gains electrons. All those added negative charges fiercely repel each other in the outer shell, which expands the radius outward, making it significantly larger than the parent atom.
Let's do our second pause check to really lock this concept in. Think about what exactly happens to a neutral aluminum atom when it loses 3 electrons to become an Al3+ cation. Why does its physical size just drop so dramatically?
So, aluminum starts out with 3 valence electrons in its outermost shell. When it loses all three, that entire outer layer is essentially gone. The remaining core electrons are now sitting in a much smaller inner shell. Plus, you still have 13 protons in the nucleus, but now they're only pulling on 10 electrons. They yank those remaining electrons inward incredibly tightly, severely shrinking the radius of the atom.
Section 5. Atomic Structure and Forces. Connecting the micro to the macro.
We've been talking a ton about the tiny positive and negative poles inside the atom, but how does this relate to the everyday physical motion you actually see and feel? Well, the micro and macro worlds map directly to each other. At the microscopic scale, the core interaction is that electrostatic pull between positive protons and negative electrons. That invisible pull is literally what holds matter together. But at the macroscopic scale, when you push a heavy box or feel friction under your shoes, you're dealing with contact and non-contact forces. Those everyday pushes, pulls, and frictional forces that determine net motion are fundamentally rooted in the electrostatic interactions of the atoms making up those very objects. It's all connected.
But quick pro tip here. We have to be a little careful. While atoms are the fundamental building blocks of forces, we absolutely cannot overstate the causation. Atomic electrostatic structure is the deep foundation, for sure, but knowing an atom's radius alone doesn't perfectly explain a complex macroscopic motion, like, say, the trajectory of a rolling baseball. You still need classical physics and Newton's laws to calculate that stuff out in the real world.
And finally, Section 6, Synthesis and Transfer, bringing it all together.
All right, let's do a rapid-fire recap of everything we just covered. Atoms are mostly empty space, built around a dense, tiny nucleus. The periodic table is basically a map. Rows show energy levels, columns show chemical behavior. For trends, atomic radius increases down a group and actually shrinks across a period. When forming ions, positive cations shrink down and negative anions expand outward. And finally, those microscopic electrostatic forces form the true foundation for the physical pushes, pulls, and friction we experience in our macroscopic universe.
Now, take this transfer question with you to think about. If you add an electron to a neutral chlorine atom to make a negative chloride anion, the atom gets larger and develops a net negative charge, right? So how will that specifically change its electrostatic pull or push on the other positive and negative ions interacting around it?
And I'll leave you with this final synthesis task. Based on what we've learned today, imagine you are using the build an atom model. Explain in 3 to 4 sentences how adding exactly one single proton to a neutral atom changes its elemental identity, its net charge, and the electrostatic forces going on inside it. It's pretty wild to think that the difference between the oxygen keeping you alive right now and a completely toxic gas comes down to just one tiny invisible proton. What else do you think is hiding in the microscopic world? Think on that, and I'll catch you next time.